All right, hello everybody, and welcome to the next Physics 121 video. Last time, what we talked about was this motional EMF, and so that's what I want to start with today, but I want to think about it from the perspective of the current that was induced. So let me remind you of what the scenario was. So first, we have already seen that if we have a constant magnetic field, so a magnetic field that's not changing, and a loop of wire, or essentially a circuit, if we change the loop area, we get an induced current. And so let me remind you of the setup. So we had a magnetic field, and let's suppose that that magnetic field is pointing into the page. And we'll assume that that magnetic field is uniform and constant. So it's everywhere the same, and its value is not changing with time. So there's our uniform constant magnetic field, B. And then what we imagined is we had some kind of loop of wire. So we had some blue conducting wire, and we were going to take a bar, and the bar is also a conductor, and we're going to pull that bar with some constant velocity, say to the right. And so in this scenario, and then our conducting tracks, our blue conducting tracks, extend out to the right. So these are conducting, let's say they're conducting rails, and this was a conducting bar. What we discovered in this case is that we would get, if we pulled this bar to the right at a constant velocity, we would get this motional EMF, and we calculated the value of the motional EMF. It was V times B times the length of the conducting bar. So this conducting bar has some length L. Okay, and what happens as a result of that induced EMF, if we use the conducting rails to make a complete circuit, then we got an induced current that went, in this case, in the counterclockwise direction. Okay, but we know that current is a source of magnetic field, and we could use right-hand rule to determine the magnetic field created by the induced current. So we take the fingers of our right hand and curl them in the counterclockwise sense, and our thumb points out of the page. And that means that there is an induced magnetic field due to the induced current that resulted from this motional EMF. And one thing we can notice is that when we increase the area of our circuit, of this loop formed by the conducting rails and the conducting bar, when that area increases, the induced magnetic field that we get opposes the external applied magnetic field, B, which was into the page. So if we increase the area A of our loop, then the I induced flows such that the magnetic field that it creates, B induced, opposes the original field B that was into the screen. Okay, I'm going to draw this picture again, but this time what we're going to imagine is that we'll keep everything exactly the same except for the fact that we're going to take our conducting rail and we're going to move it not to the right, we're going to pull it to the left. And when we pull it to the left, the area of our circuit is going to decrease. And so there's our conducting bar, and here is our conducting rails that extend out like this. And what we're going to do is we're going to pull this bar to the left. Okay, if we pull the bar to the left, what happens is the EMF changes direction because the force on the charges in our conducting bar depends on V cross B. And so if I reverse the direction of one of those vectors, then we reverse the direction of that cross product. And so the charges are displaced in the opposite direction. Okay, so that means if we have an EMF where that is negative on the top and positive on the bottom, then our induced current reverses direction so that it goes, in this case, in the clockwise sense. And so now if we do right hand rule, we curl our fingers of our right hand so that they're curling in the clockwise sense. Our thumb points into the screen and we get a B induced due to the induced current that's in the same direction, in this case, as the original magnetic field B. So if the loop area decreases, then the induced current flows such that it creates a B induced that is is in the same direction as B. Okay, so that's one observation that we've already made. You know, maybe we didn't think about it in terms of the direction of the induced current, but you know, this is motional EMF, which is a problem that we thought about already. So let's think of another possible experiment. So here's another observation that we could make. What we're going to do this time is we're going to take a coil of wire. So this is our solenoid, right? And so we take a coil of wire. And what we're going to do is we're just going to have an ammeter. So this is an ammeter. What it does is it measures the current in our wire. Okay, obviously if we just had a coil wire and an ammeter and nothing else, then the current would be equal to 0. But what we're going to do is we're going to take a bar magnet, and bar magnet has a north pole and a south pole, and so magnetic fields exit the north pole and they enter the south pole. And so first thing we do is we say, let's just take our bar magnet and we'll just place it next to our coil and do nothing else. So if we did that, we would find the following. If the bar magnet is stationary, then I induced is equal to 0. We would measure no current with our ammeter. So next, what we do is we take our bar magnet and maybe we move it towards the coil. Okay, so that's the red case. if our bar magnet moves towards the coil, we do get an induced current. And we could use the sign of the induced current from the ammeter to determine its direction. And so let's see, if we are moving the bar magnet towards the coil, what's going to be happening is we're going to increase the magnetic field through our coil in this direction, right? We're moving the north pole towards our coil. And if we do that, what will happen is we'll get an induced current that goes around our coil in this sense. And so this is going to be I induced. Now again, if we do the right-hand rule, so we curl our fingers of our right hand in the direction of the current as it flows around the coil, that means your fingers are going to be curling, they'll be pointing to the right when you look at them with your own eyes. So they're pointing to the right of the screen, and your thumb should be pointing up. And so the B induced we get as a result of the current opposes the magnetic field that is increasing in the downwards direction due to the motion of this bar magnet. Okay, so if the bar magnet moves towards the coil, we get an induced current. I induced creates a magnetic field B induced that opposes the change in the magnetic field through our coil. And so let's think about what that means. The change in the magnetic field through our coil. Initially, if the bar magnet was far away, there'd be no magnetic field in our coil. And then as we move it towards the coil, B is increasing in the downwards direction. And so to oppose that change, the induced magnetic field is in the opposite direction, and that determines the whether our induced current is flowing clockwise or counterclockwise. Okay, so let's draw that scenario again. So what we'll have is a coil. And so I'm going to try to draw the coil exactly the same. And then we go to our ammeter. And then we've got our bar magnet. It's going to be a north and a south again. So far it's identical. And what we'll do is we'll take our bar magnet, and instead of moving it towards the coil, we'll move it away from the coil. Yeah, okay, so we're going to move it away from the coil. And so, this is a velocity. If we imagine that initially our bar magnet was close to our coils, then what we would have is a magnetic field that was in the down direction, but it's going to be decreasing as we pull the magnet away. If we go back to this problem, the magnetic field in the coil is also down, but as we move the magnet closer to the coil, the strength of that field is increasing. That's the difference. The orientation of the fields are the same. It's just that in one case we have a decreasing magnetic field, And in another case, we've got an increasing magnetic. So here we have the decreasing case. And so what's going to happen is when we decrease the magnetic field strength in our coil, we're going to get an induced magnetic field that opposes that change. The induced field acts so as to try to oppose the decrease in the field. It tries to maintain the original field that we had. And so if we put our thumb down, our fingers curl in the direction that the induced current propagates. So this is I induced, and so that is the opposite direction than we had in the case above. Okay, and so what we would say in this case is B induced opposes the change in magnetic field strength in magnetic field within our coil. Okay, so it's the change that matters. In this current case, the present case, we started with a downwards field and it started to decrease. B induced acts to oppose that change, so it's in the same direction as the field. In the first case, we had again a magnetic field down in the coils, but then we started to increase the strength of that field by bringing our magnet towards the coils. B induced opposes that change, and so it's in the direction opposite of the field due to the bar magnet. Okay, so we have two different ways now of inducing currents, and one of them is to change the area of a loop in a constant magnetic field, for example. That was our motional EMF. Now we've seen that we could change the strength of the magnetic field through a loop or through a coil. There's yet another way of causing an induced current. So in this last way, what we're going to do is we're going to imagine that we've got a coil, and this is a little bit challenging to draw, but I think maybe we can do it. So here's some axis. I'm going to try to draw this with some perspective. And so this is a loop of wire. And what we're going to do is we're going to take that loop of wire and we're going to rotate it about an axis that passes through its center. And we're going to rotate it in the presence of a magnetic field. And so we're going to have a magnetic field that passes through this loop, and it looks something like this. Okay, so this is B, and we'll assume that that's a constant magnetic field, and for that matter, we could assume also that it is a uniform magnetic field. And so what we would find is that, let me change the color of my pen. If the loop is not rotating, then the induced current is equal to 0. Okay, so that's the first observation. That's just like if we go back to this problem. If I take the magnet, no matter where I put the magnet, it could be far or close or inside the coils. If the magnet's not moving, then the induced current is 0. The same thing in our original problem over here. If the bar is not moving, even though there's a magnetic field, the induced current would be 0. Okay, so whenever we have an induced current, it has to be because something is changing. Okay, so what I want to do is I want to try to draw a side view of this scenario. And so the side view is going to look like this. Side view. So this is my loop, and here's our rotation axis, and maybe we're going to rotate something like this. Okay, and then we'll draw in our magnetic field lines, and so we've got these magnetic field lines, and I'll try to draw them so that it looks kind of uniform. So here's B. We'll put in one more. I'm going to draw a line that is normal or perpendicular to our loop. And so that's not quite perpendicular. I can do better than that. Let's make a perpendicular. So this is a line that's perpendicular to the loop. And we can define an angle, and I'm going to define an angle theta that is between this perpendicular and the direction of the magnetic field, which I've drawn as horizontal. And so what will happen is the following. If our loop rotates such that theta is changing, okay, so if we change the orientation of the loop, that angle theta changes. It either gets smaller or larger. Then we get an induced current, say I induced, that's not equal to 0. If we have an I induced, there will be a corresponding B induced. Okay, so what we want to know is what direction is that induced current going to be in? If the loop rotates such that more magnetic field lines pass through the loop, then I induced acts to create a magnetic field that opposes the applied magnetic field, which we called B. So in our picture, what I want to do to get more field lines pass through my loop area is I want to decrease theta. If I decrease theta, then my loop becomes more perpendicular to the magnetic field, and so we have more field lines passing through that loop. So in the side view above, if theta decreases, then B induced is opposite of B. Okay, and that's what we kind of drew here. We would get a maybe opposite of B wasn't the right. Let's say it opposes B. So in this picture above here, what we would do is we would have a theta decreasing for the indicated clockwise rotation of our loop. That would induce a current that would make a B induced that opposes the external B, which points to the right, and so our induced B has a component that goes to the left. So if this is the wire, the edge of the wire that's closest to us, then I induced would be moving up the wire in that case and then looping around. In this picture, if we had a magnetic field that was, so I would have a B induced that would be in this direction, and we would have an I induced in this direction if we had a decreasing theta. This is the theta decreasing case. Okay. On the other hand, if theta increases, then B induced is in the direction of the external B. So what does that mean? If theta increases, then we're reducing the number of field lines that pass through our loop. And in that case, the induced current would oppose that change. It would oppose the reduction of the magnetic field lines passing through the loop. And so it would induce a magnetic field that tried to maintain what was there before the loop angle changed. Okay, so there is one nice way to summarize all of these observations. So let's recall the electric flux. So the way we calculated electric flux was we had the symbol capital Phi, and I'll put a little subscript E on here for electric flux. Maybe I should make it a capital E. The electric flux was calculated by the integral of E dot dA. So where did we use this? We used this in Gauss's law. Remember, Gauss's law said that the flux through a closed surface, so E dot dA for a complete closed surface, which we call the Gaussian surface, was equal to Q enclosed over epsilon naught. And what it did is it counted the number of electric field lines passing through some surface. For Gauss's law, it was a closed surface, but it could be an open surface. And so this could be evaluated over any surface. So similarly, we can define a magnetic flux that I'll call phi b, which has the exact same definition, but instead of E dot dA, it's B dot dA, which is B cos theta dA. So where I've made the replacement of the dot product is equivalent to B times dA times the cosine of the angle between the two. And so let me just remind you of what some of these variables mean. So I'm going to try to actually draw probably a picture similar to what we had already. So if this is our surface, some kind of closed loop, then dA is defined to be a vector that is magnitude is some patch of area, and its direction is perpendicular to that patch of area. So this is the dA vector. Let's see if I can fit it in here. dA. So the magnitude of the dA vector is the area of some infinitesimal patch of area. And so I tried to draw that here as this little square area. So that whatever that little square area is, that's the magnitude of dA. The direction of dA is perpendicular to the patch. Okay, and so then if we had some magnetic fields, and so I'll draw just a single magnetic field line, and let's suppose it's coming out in this direction, then the angle theta is the angle between dA and B. Okay, and so let's rewrite this flux expression. B, let me write it as B cos theta dA. Okay, so if you actually evaluated this integral for some surface, let's suppose that our surface has a total area A, and if we did something where we change the total area, maybe we take a wire. If this is a conducting loop, we could short circuit part of it by putting a wire over here. And so we suddenly change the area of our loop. If we did that, then we would change the magnetic flux through that loop. And we saw from the motional EMF example, the first one we thought about, if we change that area of the loop, we'll get an induced current. Okay, so we get I induced if we change the loop area. Okay, the other thing we could do is we could change the strength of the magnetic field. That's what we did in our second example. We either moved a bar magnet closer to or away from some coil or some loop of wire. And we saw that if we change the strength of the magnetic field, we get an I induced if we change B. In the third example, what we found is that if we change the angle between our loop and our magnetic field, we got an induced current. And so we get I induced if we change the angle theta. And so if you look at our magnetic flux, it involves an area. And it involves a magnetic field, and it involves the angle theta. And so what it looks like is if we do anything to change the magnetic flux through our loop, we'll get an induced current. So we can summarize all of these observations with the following statement. Any change to the magnetic flux phi b through a loop of wire will result in I induced, an induced current. This is going to be what we'll refer to as Faraday's law. Okay, we can think about this more carefully. Let's go all the way back and look at the first example. In this first example, we're moving our bar to the right. That increases the area of our loop. The magnetic flux is B cos theta times an area. So if we increase the area, we increase the flux. If we increase the flux, the induced current opposed that change. It created an induced magnetic field that opposed that change in flux. Then we decreased the area so that the flux was decreasing. The induced current acted to create an induced magnetic field that tried to sustain the flux that was already there, so it's enhancing the existing field. Over here, we took a magnetic field and we increased its strength. The induced current acted so as to induce a magnetic field that opposed that change in flux. When we pulled the magnet away, we decreased the flux through our coil, and the induced current acted so as to create a magnetic field, B induced, that tried to sustain the flux that was there originally. If we rotated our coil so that we increased the flux through the loop due to the external magnetic field, the induced current acted to create a B induced that opposed that change, to oppose that increase. If we did the opposite, if we rotated in the other way so that the magnetic flux through our loop was decreasing, then B induced would act in the other direction to try to sustain that flux. Okay, so the other thing we can say to summarize our observations is that the induced current acts to create a induced magnetic field that sustains, that, let's say, tends to maintain the original magnetic flux. This is going to be Lenz's law, which determines the direction of the induced current. So if the flux is decreasing for any reason, either you're decreasing the loop area, you are decreasing the strength of the magnetic field, or you're doing a rotation of the loop that decreases the flux, then the induced magnetic field will be in the direction of the original magnetic field to try to maintain the flux that was there originally. And so the current direction is determined by the direction that will make the induced magnetic field in the correct orientation. On the other hand, if for any reason the magnetic flux through our loop is decreasing, if it was increasing, then the induced magnetic field would be in the opposite direction of the external magnetic field. Okay, good. So maybe that's where we'll stop this video. I think what I'm going to do in the next one is I'm going to try to set up a little demo. And so I'll use that video to describe the demo, and then I'll try to make a separate video showing you the demonstration. Okay? All right, thanks very much.